So to start out probability, we need to talk about events. Simple events, compound events, and sample space. So the sample space is all the possible simple events, and a simple event is simply a outcome of an action or an experiment that can't be broken down any further. So if we're rolling a die, that's the singular of dice, in case you were curious, and we've got a six-sided die, then the possible outcomes, and this would be the sample space, the possible outcomes or simple outcomes are rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6. And each of these is a simple event. Now, it is possible also to talk about things called compound events. And compound events would be something like rolling something larger than 4, right? And in that event, there are two possible ways that you can achieve that event, right? You could either roll a 5 or a 6. Or another possible compound event would be rolling an even number, right? In this case, there's 3 possible ways to have that event occur. Okay, so these are our sample spaces, those are all of our simple outcomes, and now we can start talking about probability. So if we're rolling one of those six-sided dies, can we calculate this, let's say, the probability of rolling a 1? This notation here, p parentheses, is used to denote probability of, and so this is the probability of rolling a 1. Now, a basic probability can be computed as the number of ways that this event can occur divided by the total number of possible events. So for this particular case, how many ways can we roll a 1? Right? Remember that our sample space was this. How many of those events are rolling a 1? Well, only one of them. How many total simple events are there? How large is our sample space? 6. So there is a 1/6 probability of rolling a 1 on the die. Now, you could also write that as a percent. It's about 17%, but we'll probably be using fractions most of the time because it's a little easier. Now, how about in this one? The probability of rolling a number bigger than 4. How many ways can that event occur? Well, there's 2 numbers that are bigger than 4, so there's 2 outcomes that correspond to the event. Out of how many total outcomes are there? 6. And this is a fraction, so we can reduce it, and so there's a 1 out of 3, or 1/3 probability if you roll a die of rolling a number bigger than 4. So now let's continue talking about sort of basic probabilities. So let's say you have a bag with 20 cherries, 14 of which are sweet and 6 sour. If you pick a cherry at random, what's the probability it will be sweet? So again, we say, how many ways can, out of all of the outcomes, how many ways can our event occur? In this case, in order to be sweet, there are 14 ways that we could end up with a sweet cherry. Out of how many possible outcomes? Well, there's 20 possible cherries that we could have picked. So there's a 14 out of 20, or 7 out of 10, or if you wanted to, you could also say 70% chance, or probability that our cherry will be sweet. Now, that is, of course, assuming that all of our cherries are actually the same in shape and size. If they happen to look different, then that might not be the case. Let's look at another one. Let's find the probability of randomly drawing one card from a standard deck of cards and getting an ace. Now, if you're not familiar with the deck of cards, here's what they look like. There are 4 suits. This top one is called a spade, and then diamonds, clubs, and hearts. There are the numbers 2 through 10, an ace, which sort of corresponds with a 1, and then these 3 are called face cards, the jack, the queen, and the king. So the question was, compute the probability of randomly drawing one card from a deck and getting an ace. Well, again, we will need to say how many ways can that event occur out of all the possibilities. So there are 13 different cards for each of 4 suits. So there are 52 possible cards in the deck. Out of those, how many of them are aces? 1, 2, 3, 4. And so there is a 4 out of 52, or 1/13th, or if you wanted it in decimals, you could say 0.0769, or about 7.69% probability or chance of randomly drawing a card from the deck and getting an ace. If you pull a random card from a deck of playing cards, what's the probability it is not a heart? Now, this is what's called a complementary event, and because of the not here, so we're looking for the probability of something not happening. So sometimes we, like if E is our event, then we'll use this notation E bar for the complement of that event, which is a fancy way of saying that that event doesn't happen. So this is saying E doesn't happen. Now, because the probability of something happening is 100% or 1, then the probability of an event happening and the probability of the event not happening need to add up to 1, need to add up to 100%. And so the probability of an event not happening is 1 minus the probability of the event happening. So the probability of not getting a heart is 1 minus the probability of getting a heart. And what is the probability of getting a heart? Well, there are 13 hearts. There are 13 hearts out of the 52 cards in the deck, so 1 minus 1/4, and that would be 3/4. So there's a 3/4 or 75% probability of not getting a heart, and these are complementary events. Suppose we flipped a coin and rolled a die, and we wanted to know the probability of getting a head on the coin and a 6 on the die. Now notice that we could list out all the possible outcomes here. We could get a head, and then a 1, a head, a 2, a head, a 3, a head, a 4, a head, a 5, a head, a 6, right, on the coin and then on the die. Or we could get tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6. And so there are a total of 12 possible outcomes here. How many of them would have a head on the coin and a 6 on the die? Well, only one of them, right? 1 out of those 12, and so there's a 1/12th probability of rolling a 6 on the die and getting a head on the coin. Now, you might also notice that the probability of getting a head on the coin is 1 out of 2. The probability of getting a 6 on the die is 1 out of 6, and if we were to multiply those, we would get the 1/12th. And it turns out to be true that the probability of both events happening is the probability of A times the probability of B if A and B are what's called independent. Now, independence means that the result of the head of the coin flip does not depend or affect the result of the roll of the die. Let's look at some examples. Suppose we toss a fair coin twice. The first event is the first toss, and the second event is whether or not the second toss is a heads. Are these independent events? Yes, these are independent. Independent. Why? Because the result of the second coin toss does not depend upon the first one. The second toss has no idea whether the first toss was a head or not. How about the two events? It will rain tomorrow in Houston, and it will rain tomorrow in Galveston, which is a city near Houston. These are not independent because the cities are close together. They're likely to have similar weather patterns, and so these are not independent events. How about you draw a card from the deck and then draw a second card without replacing the first? This is, again, not independent because the result of the first draw will affect the result of the second draw. For example, if we're asking about, let's say, the probability of getting an ace, the likelihood of getting an ace on the second draw depends upon whether or not we got an ace on the first draw. So these are not independent. But if two things are independent, then we can go ahead and use that multiplication idea. So for example, in your drawer you have 10 pairs of socks, 6 of which are white, and 7 t-shirts, 3 of which are white. If you randomly reach in and pull out a pair of socks and a t-shirt, what's the probability both are white? Well, the probability of white socks is, let's see, there's 6 white out of 10 pairs, right? The probability of a white tee is, let's see, 3 of them are white out of 10. So the probability that both of them will be white will simply be the likelihood of the first being white times the likelihood of the second one being white, because the probabilities, oops, that's not right. It's not out of 10. It's out of 7, right? 3 out of 7. Sorry. So the probability of both of them being white is this. And we can simply multiply them because the probability of pulling out of the t-shirt being white is not dependent upon the probability of the socks being white. So we can go ahead and multiply that. That's 18 out of 70. In other words, there are 70 possible outcomes, and 18 of them involve both of them being white. And of course, we can reduce that fraction down to 9/35. So that's the probability that both of them are white. Later on, we'll look at how to deal with the non-independent case. Now suppose we flipped a coin and rolled a die, and we wanted to know the probability of getting a head on the coin or a 6 on the die. Now this is different than the problems we did earlier, where we were looking at for the probability of both, of the end. So, of course, the easiest way to do this for a simple problem like this is to say, well, how many of these outcomes, these 12 outcomes, how many of them have a head on the coin or a 6 on the die? And there are 1, 2, 3, 4, 5, 6, 7 outcomes that have either a head on the coin or a 6 on the die. Now, could we have figured that out another way, by sort of looking at the two events separately? So what's the probability of getting a head on the coin? So the probability of a head is 1/2, or in twelfths, right? That'd be 6 out of 12. 6 of the outcomes have a head. What's the probability of rolling a 6 on the die? Well, there's well, that's 1 out of 6, right? 1 roll out of the 6 possibilities on the die. And in terms of our total outcomes here, 2 of them have a 6 on the die. And notice if we just added these 2 up, we'd get too many outcomes. We'd get 8 out of 12. Why? Because we're counting 1, 2, 3, 4, 5, 6 for the heads, and we're counting 1, 2 for the 6s. But we've counted this value twice. So in order to compensate for that, we're going to have to subtract out that value that we double counted. So we're going to subtract out the probability of a heads and a 6, and there's 1 out of 12 there. And if we combine that, 6 plus 2 is 8, minus 1 is 7/12, and we get the same answer that we had there. So our basic rule here is that the probability of A or B is the probability of A plus the probability of B minus the probability of both. And again, we got to subtract out that and so that we're not double counting it. Let's see if we can use this. Now, suppose we draw 1 card from a standard deck. What's the probability that we get a queen or a king? Well, the probability of a queen is, let's see here, there's 4 of them out of the 52 cards in the deck. What's the probability of a king? 4 out of 52. What's the probability that the card is both a queen and a king? Well, none. It's impossible for a card to be both a king and a queen. It's one or the other. And so the probability of queen or king here is just 4 out of 52 plus 4 out of 52 minus 0 is 8 out of 52 is our probability there. Now, the reason that we ended up with this 0 here is because these two events, the probability of getting a queen and the probability of getting a king, are mutually exclusive. There's no overlaps. And so in this simple case, in this case of mutually exclusive, it turns out that the probability of getting a queen or king is just the probabilities of the queen plus the probability of the king, again, because they're mutually exclusive and there's no overlap. Now, that's not always the case, of course. So in our second problem here, what's the probability that we get a red card or a king? The probability of a red card is, let's see here, there are, half the deck is red, so that would be 26 out of the 52. What's the probability of a king? That's 4 out of 52. What's the probability that's red and a king? Now here we do have overlap because there are 2 red kings. And so for the probability of red or a king, we're going to have to add up the 2 individual probabilities and then subtract away the overlap, which leaves us with a probability of 28 out of 52 for the probability of getting a red card or a king. So here we have a table showing the number of survey subjects who have received and not received a speeding ticket in the last year, and the color of their car. And we're going to find the probability that if we were to choose one of these people at random, that that the person has a red car and got a speeding ticket, and then secondly, has a red car or got a speeding ticket. Now, if you look at the table here, there's basically 4 different categories. Here we got speeding ticket and red car, no speeding ticket and red car, speeding ticket not red, no speeding ticket not red. And then we have totals for each of the columns, totals for each of the rows, and then the total of everyone surveyed. So for the first question, where it says, has a red car and got a speeding ticket, how many people both had a red car and got a speeding ticket? Well, in this case, there are 15 of them. So 15 people both had a red car and got a speeding ticket out of how many total people? Out of 665 total people. So that's the probability of having a red car and getting a speeding ticket. Now, these are dependent events, and so we really have to work off the table. It would not be correct to find the probability of having a red car, the probability of speeding, and just multiply them. Now, how about for the next one? So here we're trying to find the probability that they have a red car or get a speeding ticket. Now, there's a couple ways that we could go about this. The easiest, honestly, is to just add up all the possibilities. So let's see here. These people got a speeding ticket. These people have a red car. So we have a total of 45 plus 15 plus 135 is 195 total people who either got a speeding ticket or have a red car, and so our probability would be 195 out of 665. Now, we could have also done this the sort of longer formulaic way and said, well, let's look at the probability that they got a speeding ticket. That's 60 out of 665. And let's add to that the probability that they have a red car. That's 150 out of 665. And then subtract the duplicates, right? Subtract those that have both, right? Our end probability here. And if we do this, we'll get exactly the same answer. But when we have a small table like this, it's probably just as easy to just count up the possibilities. So what is the probability that 2 cards drawn at random from a deck of cards will both be aces? Now, you know that the probability of pulling 1 card and getting an ace is 4 out of 52. And so it's really tempting to say the probability of getting an ace and another ace is 4 out of 52 times 4 out of 52, right? Using our multiplication rule. Now, unfortunately, this is not going to work. Why? Because these 2 events are not independent. because after we pull out our first card, after we pull out the first ace, it changes not only the number of cards in the deck, but also the number of aces in the deck, right? So now for our first draw, right, probability of ace on the first draw is still 4 out of 52. But for our second draw, this is going to change. This is now the probability of an ace on the second draw, given, and we use this little bar for given, given an ace on the first draw. And this is what's called a conditional probability. So here, how many possible outcomes, how many possible cards can one draw on the second draw? There's only 51 cards left, and so it's going to be out of 51. Now, how many aces are left? There are only 3 aces left now, and so our probability ends up being 12 out of 2652, or in other words, 1 out of 221, rather than the 4 out of 52 times 4 out of 52. Okay, so again, this is called a conditional probability. Now, let's look at another case. Let's find the probability that a die rolled shows a 6 given, so again, this is a conditional probability, given that a flipped coin shows a head. So this is the probability of a 6 on a die, given head on a coin. Now, in this case, we need to ask ourselves, are these two events independent? And the answer is yes. So in other words, this, in this particular case, doesn't matter. Why doesn't it matter? Because these are independent events. So the probability of rolling on the 6 on a die is the same as always. It is 1 out of 6. Let's look at one more case now. Let's look at a table of values here. These are the speeding ticket folks. So let's find the probability that they have a ticket given that they have a red car. So now we're given that they have a red car, so we know right away that we're only talking about these 150 people. So we're only talking about out of these 150 people. Now, out of those 150 people with a red car, so we already know that, how many of them got a ticket? Well, 15 of them got a ticket, so that's 15 out of 150, or 1 out of 10, or 10% of people with a red car also had a ticket. Now, different question now is, what's the probability that they have a red car given that they have a ticket? Now, this is not the same thing, because now we're limiting ourselves to these 60 people. So we have 60 people total who got a speeding ticket. How many of them had a red car? 15 of them had a red car. So 15 out of 60, or 1/4, or 25% of people with a speeding ticket had red cars, right? So these are the conditional probabilities, and it is important to notice here that the order here does matter. It does matter which piece of information you're being given. So let's look at a couple more conditional probabilities. Suppose you pull 2 cards out of the deck. What is the probability that both are spades? So the probability that the first card is a spade, well, let's see here. There are 13 spades out of the 52 cards in the deck. So that's the probability that the first card is a spade. So now, what's the probability that the second is a spade, given that the first was a spade? Right? In order for both cards to come out spades, the first is going to have to be a spade and the second. And so, what's the probability that the second one is a spade given the first was? Well, in this case, given that the first one was a spade, then there's now one less card in the deck and one less spade in the deck. And so 12 out of 51 is the probability of the second one being a spade. So if I want to find the probability that both are a spade, I'm going to use the conditional probability version of the multiplication rule, which says that the probability of the first event happening times the probability of the second event happening given that the first happened. So in this case, 13 out of 52 for the first spade, 12 out of 51 for the second spade, gives us a probability, gives us a probability of 156 out of 2652, or 1 out of 17, or about 5.9% probability of getting two spades when we draw two cards. Let's look at another one. If you draw two cards from the deck, what's the probability that you'll get an ace of diamonds and a black card? Now, this one's a little trickier because the events are different. So there's two different ways that this could happen. Either we do the probability of the ace of diamonds, then the black card, and then separately we need to consider the probability of getting a black card, then the ace of diamonds. Because it's sort of hard to think about putting those two cases together. So here, we're going to find the probability of the ace of diamonds, then the probability of getting a black card, given that we already pulled the ace of diamonds. And then for this case, we're going to find the probability of getting a black card, then for the second event, the probability of getting the ace of diamonds, given that we already pulled a black card. Okay, so first case here, what's the probability that we pull the ace of diamonds? Well, there's only one of them out of the deck, so 1 out of 52. How many ways could we pull a black card, given that the first card was the ace of diamonds? Now, given that the first card was an ace of diamonds, there's one less card in the deck. But diamonds are not black, so there are still 26 black cards in the deck. So our probability here ends up being 26 out of 2652 is 1 out of 102. Here, the probability of getting a black card on the first draw is 26 out of 52. Here, the probability of getting an ace of diamonds, given that the first card was black, if the first card was black, then there's one less card in the deck, but we know the ace of diamonds is still there, so there's still one of them. And so we end up with 26 out of 2652 is 1 out of 102. So in both cases, the probability is 1 out of 102. These are two different ways that the same result could happen. So we need to add these together. And so the total probability of getting an ace of diamonds and a black card is the sum of those, 2 out of 102, or 1 out of 51. So this looks at sort of an important application of conditional probability. So here we have a home pregnancy test that was given to women, and then pregnancy is verified through blood tests. And then this table shows the home test result up here, and then whether they're actually pregnant or not down here. So we're going to compute two different conditional probabilities. First, the probability that they're not pregnant, given that they have a positive test result. So this is, you have a positive test result, and then what's the likelihood that you're not actually pregnant? So here, we're given that we have a positive test result, so we're limiting ourselves to these 75 people, and of them, 5 are not pregnant, and that's about 6.7%. So there's about a 6.7% chance here that this person's not actually pregnant, given that they have a positive test result. Now, let's look at the next one, which is the probability of a positive test result given that they're not pregnant. So here's somebody here's all 19 people who are not pregnant, and out of them, 5 of them have a positive test result. So this is what's called a false positive. This is when somebody who doesn't actually have the condition gets a positive result anyway, so it's an accidental positive result. And you'll notice that this probability is substantially different. This is about 26.3% here. And it's really interesting to note that these results are quite different. So even though this test has a 26% false positive rate, that means 26% of the time it will tell somebody who's not pregnant that they're pregnant, that is not the same probability as once you actually have a positive test result, whether or not it is whether or not you're actually pregnant. Now, admittedly, this data is made up, but this basic idea does hold true for pretty much all tests of disease, and it all depends upon the incidence rate, how likely it is that you actually have either the disease or, in this case, the likelihood of being pregnant. So now we're going to look at a sort of more complicated testing situation, and this one fouls doctors up, so we'll walk our way through this. So suppose a certain disease has an incidence rate of 0.1%, that is, it afflicts 0.1% of the population. In other words, the probability of having this disease is 0.001, 0.1%. So a test has been devised to detect this disease. The test does not produce false negatives. In other words, anyone who has the disease will test positive for it. In other words, the probability of a positive test, given that the person has the disease, is 100%. They will definitely test positive if they have the disease. But the false positive rate is 5%. This means that the probability that somebody will test positive if they do not have the disease is 5%. So 5% of people will test positive even if they don't have the disease. So now if we randomly pick someone, what's the probability that they actually have the disease? In other words, what is the probability of the disease given that they test positive? And as we saw before, this is not going to be the same as the probability of a positive test given the disease. So let's work our way through this. So here I've broken down all that information again. So to think about this most simply, let's imagine that we have 1,000 people. Now, because the disease incidence rate is 0.001, or 1 out of 1,000, then that tells me that out of these 1,000 people, one of them will have the disease, and 999 of them will not have the disease, on average. Now, if they have the disease, we know that they're going to test positive, and so this one person is going to have a positive test result. There are no people who have the disease and test negative. But now, out of these 99 people who do not have the disease, we know that 5% of them are going to test positive. So 5% of our 999 people is 49.95, or about 50. So let's just call it 50. So 50 people are going to test positive who don't actually have the disease, and the other 949 are going to test negative. So that leaves us 51 people testing positive for the disease. Now remember, what we're really interested in is what is the probability that you have the disease given that you tested positive. Well, now we have enough information to figure that out. How many people tested positive? 51. How many of them actually have the disease? 1. And that comes out to about 1.96%. So, remarkably, even though this test has no false negatives and only a 5% false positives rate, if you test positive for this disease, there's only a 2% chance that you actually have it. And that should be surprising, but that is the result of our probability. So now we have another disease that has an incidence rate of 2%. The false negative rate is 10%, false positive rate is 1%. So let's compute the probability that a person who tests positive actually has the disease. So there's two ways to do this. Let's start with the easy way, and that is to create a table. So now we got positive, negative, disease, no disease. Now, for simplicity, let's imagine that we have some nice round number of people. Let's go with something pretty big, like 10,000, just to make sure our numbers work out okay. So now we have a 2% incidence rate. So out of these 10,000 people, 2% of them, or 200 of them, will have the disease. Meanwhile, the other 9,800 of them will not have the disease. Now, we have a false negative rate of 10%. And so that tells us that 10% of these 200 are going to incorrectly test negative. Meanwhile, the other 180 will correctly test positive. Meanwhile, we have a false positive rate of 1%, and that means that out of our people who don't have the disease, 1% of them, or 98 of them, are going to test positive. Meanwhile, the other, let's see, 9,702 of them are going to correctly test negative. So notice these here, these 98 people here, and these 20 people here are errors, right? So altogether, we have 278 people testing positive. So if we wanted to find out the probability that they have the disease, given that they test positive, then we have 278 people who tested positive. Of them, 180 have the disease, and that comes out to be about 64.7%. So about 65% of people who test positive, in this case, will actually have the disease. Now, there's another way we could go about this problem, and that would be using Bayes' rule. So let's take a look and see what that would look like. So Bayes' rule says that the probability of A given B is the probability of A times the probability of B given A over the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. Now, in terms of our disease, that would look like this. So now we can start filling in all this information. So, what is the probability that they have the disease? Well, that is, in this case, 2%, right? It's a 2% incidence rate. What's the probability that they get a positive test given that they have the disease? Well, there's a false negative rate of 10%, which means there's a 90% chance that they'll test positive given they have the disease. Down here, we got, let's hear again, probability of disease, probability of positive given disease, probability of no disease would be 98%. And then what's the probability that we test positive given that we don't have the disease? That's our 1% false positive rate. And if we compute all that out, it turns out to be 0.018 over 0.0278, which comes out to the same 64.7%. We came up with using our nice little table. So this Bayes formula has its advantages, but for a lot of cases, working off the table like we did first is going to be a simpler approach. So now we're going to talk about counting for a while. And you're probably thinking, counting? I don't know how to count. But we're going to talk about counting really large amounts of stuff. So here's an example. Suppose a restaurant, you have 3 choices of appetizer, 5 choices for a main course, and you're allowed to choose exactly 1 from each category. How many different meal options do you have? Well, there's several ways to approach this. One way that I like is called a decision tree. So you start out here and say, okay, I have how many choices for my appetizer? I have 3 choices. So I have 1, 2, 3 different directions I could go. I could go soup direction, salad direction, and then breadsticks direction. Then, at each of those points, I now have to decide on a main course. And for each of those, I now have 1, 2, 3, 4, 5 choices emanating out. And so how many total choices do I have now? You'll notice that there are 5 choices here, another 5 here, another 5 there. We end up with a total of 15 choices, and that is how many meal options we have. Now, you may have noticed that where does that 15 come from? Well, it's 3 choices for our first decision times the 5 choices for the second decision, because we have 3 of these little branchy tree things. So we end up multiplying those choices together. And that's exactly how this works. So let's look at another one. Suppose there's 21 novels and 18 volumes of poetry that you on a reading list for an English course. How many different ways can you select 1 novel and 1 volume of poetry? Well, there's 21 choices for the novel, 18 choices for the poetry. We multiply those together, and that gives us a total of 378 possibilities. Let's look at another one. Now, suppose that we're at a restaurant and we have 3 choices for the appetizer. We have 5 choices for a main course, and now 2 choices for dessert. If we're allowed to choose exactly one of them, one of each of them, then we would have 3 times 5 times 2 equals 30 choices. Now, it is important to note here that this is assuming that we actually pick one from each of them, then we're not going to, not pick one of them. Okay, one more. So suppose a quiz consists of 3 true or false questions. How many ways can a student answer this? Well, so we have 3 questions. Each of those questions has 2 choices, right? So the first question, right? So 3 questions. The first question, there are 2 choices. For the second question, there are 2 choices. For the third question, there are 2 choices. And so altogether, there are 2 to the third, or 8 different ways that a student could answer a 3-question true or false quiz. So how many different ways could the letters of the word math be rearranged to form a 4-letter code word? So we have 4 letters, and we can ask ourselves, how many choices do we have for the first letter? Well, we have 4 choices. How many choices do we have for the second letter? Now, we're rearranging the letters, so we can't use any letters twice, and so there would only be 3 choices for the second letter. How about for the third letter? 2 choices, and then there's only 1 choice for the last letter because there's only 1 letter left. And so we'd end up with 24 different code words that we could create out of the letters of math. Now, notice that's different than saying use the letters from math and you can have repeats. If we could have repeats, we'd have 4 times 4 times 4 times 4, or 4 to the 4th, different code words, and that'd be 256 different code words. We'd have a lot more if we allowed repeats, but here we're not allowing repeats. We end up with 24 possibilities. Now, this sort of computation is done so often that we come up with a shorthand notation for it, called the factorial. Factorial. In general, the idea is that n factorial means that number times 1 less times 1 less times, keep on going down all the way down to till you get down to 1. So it's multiplying numbers in decreasing order till you get down to 1. So this is 4 factorial, 4 times 3 times 2 times 1. Okay, let's look at another problem. How many ways can 5 different door prizes be distributed among 5 people? So we've got 5 people, and we got 5 different prizes. So how many choices are there for the first person? 5. How about for the second? 4, 3, 2, and 1, or in other words, 5 factorial. And if you can find the factorial button on your calculator, it'll make your life a little easier here than hitting multiplication, 5 times 4 times 3 times 2 times 1. But either way, we come up with 120 different ways to distribute those prizes. Now let's look at a slightly different one. Charity event is attended by 25 people, and we're going to give away 3 prizes, and they're different prizes. No person receives more than 1 prize. How many different ways can we distribute these? So we only have 3 prizes, and the order does matter because it matters who gets the $100 prize versus who gets the $25 prize. So how many choices do we have for the first prize, for the $100 prize? Well, there's 25 people, so there are 25 possibilities for that prize. How about for the second one, for the $25 prize? Well, there's no repeats, right? No person receives more than 1 prize, so there's only 24 people now. And for the last prize, for the $10 prize, there's 23 people. And so we end up with 13,800 different ways that these prizes could be awarded. And you'll notice that this looks awfully similar to our factorial that we were doing earlier, but truncated, right? Where we don't go all the way down to 1. And it turns out that there is a nice way to represent this, which we'll look at in a minute. Let's look at one more first, though. 8 sprinters have made it to the Olympic finals, 100 meters. How many different ways could the gold, silver, and bronze be awarded? Or how many different possible outcomes are there, basically? So, similar to the last problem, there are 8 possibilities for the first place, for the gold. There are 7 possibilities for the silver, and there are 6 possibilities for the bronze. That gives us a total of 336 different orderings, or 336 different outcomes. So I have 9 paintings and room to display only 4 of them on the wall at a time. How many different ways could I do this? So I'm going to presume that ordering matters here. In other words, I care what order the pictures are in, and that I can't use the same picture twice. So we certainly could answer this question by saying, how many choices do I have for the first one, the second one, the third one, and the fourth one? And we could certainly do that and end up with our answer, 3,024 different orderings. Now, we're going to try to come up with another way to do this, and this thing is what we call a permutation. A permutation is a rearrangement of items where order matters, and we're selecting from a group. The usual notation is NPR, where N is the number of items, number of choices, and then R is how many we're going to pick, the number we pick. So R is the number we pick from our total number of choices. So this problem here would be 9P4. We have 9 choices, and from them we're going to pick 4 of them, and we're going to look at all the possible orderings or permutations of them. Now, there's several ways to calculate a permutation. One is the way we just did it, which is to just multiply 9 times 8 times 7 times 6. Another way to do it is to use factorials. You'll notice that this looks a lot like 9 factorial, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but it's not as much, right? We don't have the 5, 4, 3, 2, 1. So we can get rid of that by dividing by 5 factorial, which will then reduce all of those away, leaving us with just the 9876. So if we have NPR, it turns out we can compute that using factorials as n factorial over n minus r factorial. So in this case, when we had 9p4, that would be 9 factorial over 9 minus 4 factorial, or in other words, 9 factorial over 5 factorial, as we just saw here. The other way you can do this is if your calculator happens to have a permutations feature on it, you can ask it, what is 9p4? And it should spit out this 3024 answer for you. Now, this is kind of handy when we're looking at larger numbers. So let's look at one more example. How many ways can a 4-person executive committee, president, vice president, secretary, treasurer, be selected from a 16-member board of directors? So in this case, there are 16 choices, 16 members on the board of director, and from them, we're looking at permutations of size 4. So we're looking at orderings. Again, order matters here because it matters who's chosen as president and vice president versus the other way around. So 16 people, we're picking 4 of them, order matters, 16p4. Now, again, we could either compute this as 16 times 15 times 14 times 13, or 16 factorial over 16 minus 4 is 12 factorial, or we could pull out our calculators. Either way, we're going to end up with 43,680 different executive committees. So a charity event now is attended by 25 people, at which 3 $50 gift certificates are going to be given away as door prizes. How many ways can we do this? Now notice that all 3 prizes are the same here. So we could go with the basic idea of saying, okay, we have 3 people, there are 25 possibilities for the first prize, 24 for the second, and 23rd for the third. Or in other words, there are 13,800 different ways that we could pick 3 people from our crowd. Now, let's imagine now that we have 3 people. We're just going to call them A, B, and C for simplicity. So if A, B, and C were picked first, second, third, that would be one of these 13,800 possibilities. But if B was picked first, then A, then C, then this would also be one of those one of those 13,800 possibilities. But really, these are the same outcome. In fact, there are 6 different outcomes. There are 6 different outcomes that are all really the same outcome because order doesn't matter here. It doesn't matter who's chosen first, second, or third. So in order to compensate for this, we end up needing to take our 13,800 different permutations and divide it by 6 to come up with 23,000 what are called combinations. Combinations are what we call it when order doesn't matter. In other words, it doesn't matter who is chosen first. Now, the way we can sort of generalize this is the idea of the total number of permutations, so NPR, divided by, well, where did the 6 come from? That's the number of different ways of ordering 3 people. So in this case, it was 3 people, 3 possibilities for the first person, 2 for the second, 1 for the third. That is 3p3. Or in general, this would be RPR. And this is how we define a combination, or how we calculate combinations, and we denote combinations with NCR. So this is from n choices. We're choosing r of them, but the order doesn't matter. So we're going to count ABC the same thing as BAC. This is one way to compute it. The other way is using factorials, and that looks something like this. So now let's look at an example. So A group of 4 students is to be chosen from a 35-member class to represent the class on the student council. Now, order doesn't matter here because they're all just representatives. So in this case, from our 35 students, we're going to choose 4 of them, but the order doesn't matter, so this is a combination. So, using our sort of first version here, the permutation version, we're thinking from 35, how many different ways can I pick 4 people if order did matter? And then I'm going to divide that by the number of ways of ordering 4 people. So this says, from 35 people, I need to pick 4, so I got 35 choices for the first person, 34 for the second, 33 for the third, and 32 for the last choice. And then I'm going to divide that by the different ways of ordering 4 people. So then I have 4 choices for the first person, 3 for the second, 2 for the third, and 1 for the last. So this is the total number of ways of choosing 4 people if order matters, divided by the number of ways of ordering them, which takes care of the order, gives me 52,360 different combinations. So the Senate Appropriations Committee consists of 29 members, and suppose that it was 15 Republicans and 14 Democrats. The Defense Subcommittee, which is a smaller group of that, consists of 19 members, 10 Republicans and 9 Democrats. How many different ways could the members of the Defense Subcommittee be chosen from among the 29 senators on the Appropriations Committee? So you can see that we're going to look separately at the Republicans and the Democrats here. Okay, so for the Republicans, we have 15 Republicans overall, and 10 of them are going to end up on this subcommittee. So from the 15 Republicans, we're going to pick 10 of them, and order does not matter, so we're going to use combinations. And that turns out to be 3,003. For our Democrats, we have 14 Democrats altogether. 9 of them are going to end up on our committee. So 14 choose 9, and that comes out to be 2,002 different ways. But then how about for our entire committee here? So now imagine that let's put all the Republican choices on little slips of red paper. So we got 3,003 pieces of red paper, and then we put all 2,002 Democratic choices on little slips of blue paper and threw them all in a hat. How many ways could we pick 1 red slip and 1 blue slip? Well, there's 3,003 possibilities for choosing a Republican contingent, and there's 2,002 choices for choosing a Democratic contingent, and so we simply multiply those together just like our restaurant choices, and we end up with a very large number, over 6 million different ways of selecting the members of the subcommittee. So now we're going to compute some probabilities using counting. So a 4-digit PIN number is selected. What is the probability that there are no repeated digits? So that would mean that all the digits have to be different. So if I was going to pick 4 digits where all the digits are different, I would have 10 choices for the first digit, assuming we're allowing values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 choices for the first digit, 9 for the second digit because we're not going to allow repeats, 8 for the third digit, and 7 for the fourth digit, or in other words, that's 10p4, right? Is 5,040 different pins with no repeats. Now, in order to compute the probability, we're going to have to find the total number of pin numbers, including repeats. So all pins. So if we consider all pins, that including allowing repeats, how many choices are there for the first number? 10. How many for the second number? Also 10, also 10, also 10, because we allow repeats, so there's no exclusions. So that's 10 to the fourth, and 10 to the fourth is 10,000. So there's 10,000 total pins. Out of those, 5,040 of them have no repeats. So we got 5,040 out of 10,000, or about 50.4% of pins have no repeated digits. So now let's look at a lottery problem. So in a certain state's lottery, we got 48 different numbers, and 6 of them are drawn at random. And if you have, the player gets to choose 6 numbers, and if their 6 numbers match, they win $1 million. And the order doesn't matter in this particular lotto, so we're not playing Powerball. And let's see if we can find the probability that we win that $1 million prize if we purchase a single ticket. So the first thing we need to know is how many possible outcomes are there. So from 48 different numbers, we're going to choose 6 of them, and order here does not matter, which is why we're using combinations. And so we end up with 12,271,512 different 6-number outcomes. Now, if you have one ticket, then you have one outcome, and so your probability of winning is 1 out of 12,271,512, which is a really, really small number. And so that's the probability of winning the main prize. Now, oftentimes there's a second prize, and in this case, it's $1,000 if you can match 5 of the numbers. Now, there are still 48 choose 6, 12,271,512 different outcomes, but now we need to figure out how many of those involve us winning, matching 5 of the numbers. Now, in order for that to happen, from our 6 numbers on the card, we're going to have to match 5 of them. So how many different ways can we pick 5 matching numbers out of our 6? That would be 6 choose 5, which is 6. Now, we also have to consider that, how many different ways could we not pick the last number. So from the 42 non-winning numbers, we need to pick one of them to be on our card, and so that is 42. So our final probability of winning is going to be, there are that many. 42 times 6 is 252 different ways that we can match 5 numbers and not match the 6. Out of our 48 choose 6, out of our 12,271,512 total outcomes, and that gives us a, marginally higher probability of winning, though it's still pretty small. So now suppose we randomly draw 5 cards from a deck. What's our probability of getting exactly 1 ace? Now, in order for us to get exactly 1 ace, then from the 4 aces in the deck, we need to pick one of them. One of them needs to be in our hand, in our set of 5 cards. And there are 4 different ways that can happen. And then from the remaining 48 non-aces, we're going to need 4 of them. Because in order for us to have exactly 1 ace, we need to have 1 ace and 4 non-aces. So this is 1 ace, and then this is picking 4 non-aces. Now remember, we're doing counting here, so we're figuring out how many ways can I pick 4, 1 ace out of 4, and how many ways can I pick 4 non-aces out of 48? And there are a fair number of ways of doing that. So our final probability, our probability of exactly 1 ace, is 4 choose 1 times 48 choose 4. Again, that's picking 1 ace and 4 non-aces out of all the ways of picking 5 cards. That's 52 cards. I choose 5 of them. Altogether, that comes out to be about 778,320 out of all 2.5 million hands, and it turns out to be about 0.299, or in other words, there's about a 30% chance that out of 5 cards, one of them, exactly one of them, will be an ace. So now, what if we wanted to find the probability out of a 5-card hand of getting exactly 2 aces? So this is going to be very similar to the last one. Here, out of the 4 aces in the deck, we're going to need to pick 2 of them, and out of all the non-aces in the deck, we're going to need to pick 3 of them this time, right? So we have a total of 5 cards, 2 aces, 3 non-aces, and that's out of all the ways that you can choose 5 cards out of 52. And that turns out to be about 0.0399. So there's about a 4% chance that out of a 5-card hand, that you'll have exactly 2 aces, a pair of aces, in that hand. So now we're going to look at sort of a notorious problem in probability called the birthday problem. So suppose that 3 people are in a room. What's the probability that there's at least one shared birthday among these 3 people? So now this idea of at least one is kind of tricky. So the way we're going to tackle this is the idea that the probability of at least one is easiest to think about through its complement. So what is the complement of at least one shared birthday? Well, the opposite of at least one shared birthday is no shared birthdays. And so that's the probability we're going to try to find. So let's see, in order for there to not be any shared birthdays, then each person is going to have a different birthday. So for the first person in our group, how many different ways could we pick their birthday? Well, they would have 365 choices. We're going to ignore leap years here. Out of the 365 choices for the year. Now, the second person, in order for them to have a different birthday, then out of the 365 days in the year, they're going to have a different one. So they only get 364 choices. And then our third person in the room is only going to get 363 choices. And so this is the probability of no shared birthday, the probability that each person has a different birthday. And this turns out to be, you'll notice that this first fraction is actually equal to 1. So this turns out to be about 0.9918. Again, that's the probability of no shared birthday. So the probability of at least one shared birthday is 1 minus that. Is, pretty small. It's about, 0.8%. Not too big. Let's make our group a little bit bigger now. So suppose we've got 5 people in the room. So then the probability of at least one shared birthday, again, will be 1 minus the probability of no shared birthdays. In order for that to happen, again, the first person gets, can pick any day they want. They aren't, of course, actually picking, but you know what I mean. There's 365 different ways that this person could have a birthday and not conflict with that person. And we do this for each of our people in the room. And that would give us our answer. Turns out to be about 2.7%. But we could simplify this a lot if we notice that the denominator here is 365 to the we see that this is just 365 P5. So from 365, there's how many ways can we pick 5, or how many orderings are there? And in the bottom, we've got 365 multiplied together 5 times. That's 365 to the 5th power. And computing that, we get exactly the same answer that we had there. Now, this is really cool, because now if we ask the question, what happens if we put 30 people in the room? What's the probability of at least one shared birthday? We can answer this pretty easily, because we can say, well, it's 1 minus the probability of no shared birthdays. No shared birthdays mean from 365 possible birthdays, we're going to how many ways could we pick 30 different birthdays out of, from 365, how many different ways could there be 30 birthdays, including repeats, right? And that's the same idea as our numerator and denominator there. And computing that, that comes out to be 0.706, or 70.6%, which is probably a little bit surprising. That means out of 30 people in a room, there's a 70% chance that there's at least one shared birthday in that room. So in the game roulette, a wheel with 38 spaces, 18 red, 18 black, and 2 green, is spun. In one of the possible bets, a player bets $1 on a single number. If that number is spun on the wheel, then they receive $36, their original dollar plus 35 additional. Otherwise, they lose their dollar. So on average, how much money should a player expect to win or lose if they play this game repeatedly? So for winning, let's first talk about the probability of winning. If they bet on any one number, their probability of winning, is 1 out of 38. So then for losing, the probability of losing is the complement of that. So there are 37 ways that a player can lose. Now, to compute this idea of expected value, and we're talking here about sort of your expectations, then we can compute that expected value by multiplying the probability of winning times the value of winning, and adding to it, or subtracting from it, the probability of losing times the value of losing. So for winning, the value of winning is a positive $35. So we get $35 more than we started with if we win, and the probability of that happening is 1 out of 38. We're going to add to that the other outcome, which is losing, and that outcome has a value of negative $1. In other words, we lose $1, and that happens with probability 37 out of 38. If we add those together, we end up with 35 over 38 minus 37 over 38 is negative 2 over 38, or in other words, about negative 0.053. So in other words, if you were to play this game, you should expect, on average, to lose about 5 cents per spin. So in other words, if you played for hours and played for thousands of spins, on average, you should expect to lose about 5 cents per spin. Sometimes you'll win, sometimes you'll lose, but on average, you'll lose about 5 cents per spin. So now let's look at a lottery problem. We looked at this lottery before, and we figured out that the probability of matching all 6 numbers was 1 out of all the possible choices. So it was 1 out of the ways of picking 6 numbers out of 48, which was 1 out of 12 million-ish. And the probability of matching 5 was, let's see here, we had to, from 6 numbers, we had to pick 5, and then from the 42 non-winning numbers, we had to pick 1, and we ended up with a probability of about 252 out of, again, that 12 million there. So now let's think about values. So this thing has a value of positive $1 million. This outcome has a value of positive $1,000. And then, of course, there's the probability of not matching anything, which is going to happen the rest of the time, right? So 1 minus the 253 out of 12,271,512. And this has a value of negative $1, because it costs $1 to play. So to compute our probability here, we're going to multiply this probability times this outcome, this probability times this outcome, and this probability times this outcome, and add those up. And when we do, we get a value of about negative 0.898. In other words, if you play Lotto a whole bunch, you should expect, on average, to lose about 90 cents per ticket. Of course, most people lose their dollar, and only a few people actually win anything. But on average, you should expect to lose 90 cents. Okay, a 40-year-old man in the US has about a 0.242% risk of dying during the next year. An insurance company charges $275 for a life insurance policy that pays a $100,000 death benefit. In other words, it pays that if the person dies during the year. Otherwise, they just get their $275 and the person doesn't get anything. So what is the expected value for the person who's buying the insurance? So there's two possible outcomes here. So outcome number one, of course, is dying, and outcome number two is not dying. And each of those has an associated probability. The probability of dying, presumably, is 0.00242, and the probability of not dying, then, is the complement of that, which is 99758, right? 1 minus the probability of dying. And then the value of the outcome, well, the value of dying, and I know we're purely talking monetary values here, of course, not emotional values or life value, purely monetary. Then for the person buying the insurance and their family, the value of to them is the $100,000 they get minus the $275 they had to pay for the policy. So they have a positive net benefit of $99,725. If they don't die, then the financial value of the insurance is a negative $275. So our expected value then, is the probability multiplied by the value of the outcome plus our other probability times the value of its outcome. And altogether, that gives us a negative value of 33. In other words, if we had a bunch of people, thousands of people, who are, thousands of 40-year-old men, then on average, the men will have lost $33. Now, it's not surprising that this value is negative. That's the only way the insurance company can afford to offer policies. I mean, that $33 on average is what's paying for their expenses, and profits and everything else that goes into a business, for the agents and everything else. And really, the reason that they can afford to pay out that occasional $100,000 benefit is because of all the people who don't die who balance it out. So even though this has a negative expected value to the purchaser, there's certainly security, knowing that your family's cared for, benefits to having insurance, which might make that expense worthwhile.